Okay, so next I'm going to show you a trick you can use to solve multiple systems at once in a very particular situation, as we'll see in an example afterwards. So let's say you start with an invertible matrix A. Well, then it follows from the fundamental theorem of invertible matrices that any matrix equation you form using A as the coefficient matrix, so you can take your constant matrix B to be anything you like and it's guaranteed to have a unique solution. That's a property of invertible matrices. So this is going to have a unique solution for any n by 1 matrix B that you possibly put here. So, well, what if you have several choices of this constant matrix? What if I have B1, B2 all the way up to Bm? I'll go through the rest of this after. Let's say you had B1, B2 all the way up to Bm as possible choices for this constant matrix B. Well, for every single one of these options that you put in for B, you're going to get a different matrix equation. So that's what brings us to our next remark. It follows that if A is an invertible n by n matrix and B1, B2 all the way up to Bm are your n by 1 choices for this constant column, then each of the linear systems, let's write out the matrix equations for these linear systems. You have Ax equals B1. That's one linear system. If you take your first option, B1, to put there, what if you put your second option, B2, to go there? Well, you'd have the following. You'd have Ax is equal to B2. And all the way on to the very last one, Ax is equal to your final constant column, Bm. So if you take all these different options and plug them in for B, you're going to get a different, potentially a different linear system for every single one of them. So each one of these has a unique solution because A is an invertible matrix. So how would you find them? Let's say you were actually given an invertible matrix A, and I actually gave you constant matrices B1, B2 all the way up to Bm. So let's assume you actually had the values. We're not working abstractly here. We're working with actual values. How would you find the solutions? Well, one option would, and it says it right here, these solutions may be found separately by reducing the augmented matrices of each linear system. So what would the augmented matrix of this linear system be? Well, you'd have A and then B1. That's the shorthand we use for the augmented matrix of a matrix that corresponds to the linear system that underlies this matrix equation. So that would be the augmented matrix for the first linear system. And then you could solve this you could reduce this augmented matrix here, which is the augmented matrix of the linear system that underlies this matrix equation. And you could do that for each one. So let's complete the list. So the last augmented matrix for this linear system, you'd have A, Bm. Right? You could reduce each one of those separately and treat it as a separate problem. And it'd be a lot of work, right? Because even if A was like a 3 by 3 matrix, and this was like 3 equations and 3 variables, there's still plenty of work sometimes to reduce it, especially if the numbers don't work out that nice and you end up having a fraction floating around. That can make these still a fair amount of work. So you're going to do a lot of work potentially to solve this one, only now have to go to the very next one in the list and now solve that one. And then once you finally solve that one, then go to the next one in the list and finally solve that one. It's quite a lot of work, what's being described here in this process. But if you think about it, what steps would be involved in reduce? Let's just look at the first one. What steps would be involved? Well, you're going to do row operations until A turns into the identity. And you know that's going to happen if A is invertible. You know that's what solving the system is going to look like if you have a unique solution, which we already know in advance. We've addressed the fact that we know we will. So you're going to gradually turn this into the identity matrix. And then you're going to get the solution that way. What do you do when you get to this one? What are you going to do? Generally speaking, you're going to try to turn this matrix A into the identity matrix. But it's the same coefficient matrix that you had here. So the row operations that you use are going to be identical. So you could just keep track of the row operations you did here, and you know you're going to do the exact same row operations over here. But even then, even that still would be doing more work than you need to do. Okay, and here's what you're going to do instead. So here's the alternative, and here's the guts of this discussion. Alternatively, the solutions may be found simultaneously. This is the key, by reducing a single augmented matrix. And this is a new one we haven't seen before, but this is what it looks like. You start off the same. Right, so I start off as if I'm just writing down this augmented matrix, and then I get to here, but instead of closing the bracket, I just draw another vertical line, and then another vertical line, and I keep going until I list all of the constant columns of all these systems. So I just take all the constant columns, paste them on afterwards together, and I only need one copy of A because it's the same coefficient matrix for every single linear system. So the idea is now I still am going to perform row operations to turn this into the identity, but I'm also going to perform those row operations on all of these columns as well. And that's how I'm going to get the solution to all of these linear systems at once. So I'm going to show you an example where we have two linear systems, and the key is to solve these systems simultaneously, this approach works only if, first of all, your coefficient matrix is invertible. And really, we don't know that until we actually try, right? You don't know that always in advance that it's going to be invertible. But what you do know is that the coefficient matrix for both of these linear systems is the same, right? You can check the left-hand sides of these equations are equal to the left-hand sides of these equations. And because of that, we can solve this linear system, both of these linear systems at once. So that's what we're going to do here. So let's form this matrix. Okay, so let's form the equivalent of this matrix. So we're going to write down the coefficient matrix of our linear systems. So we've got 1, 2, 3, right? Because 1, 2, 3, 2, 5, 3 for the second row. And then our third row is 1, 0, 8. Then I'll draw a vertical line, and then I'm going to draw my constant column. Now this is where I would just, typically if I was just working on this system, I would close the bracket here, and I would shut this off. But I'm not. I'm going to draw a vertical line, and then now I'm going to write a constant column for this matrix, or for this linear system over here. So I've got 1, 6, and negative 6. So that's this, you can call it a special augmented matrix. It's essentially this structure here, but in our case m is equal to 2 because we only have two linear systems to worry about. So it's really just our coefficient matrix and then the two constant columns from both of the linear systems, and then we close the bracket off here because that's all we had. So that's what we have here. And now all your focus is just going to be over on here like it normally would be. We're going to just start trying to turn this into the identity matrix. So if we do Gauss-Jordan elimination, we're going to first get rid of these two entries here. So let's take, I can't resist, I just want to use a different color here. So we're going to go row 2 is replaced with row 2 minus 2 row 1, and then row 3 is replaced with row 3 minus row 1. Okay, so what are we going to get if we do that? So the first row won't change. We'll have 1, 2, 3, 4, and 1. And then what about our second row? We're going to subtract row 1 twice, so 2 minus 2 times 1 is 0. 5 minus 2 times 2, that's going to be 5 minus 4. 3 minus 2 times 3, that's going to be negative 3. What about this? 5 minus 2 times 4, that's going to be 5 minus 8, which is also negative 3. And then lastly, 6 minus 2 times 4, that's going to be 6 minus 2, which is 4. Okay, so that's our second row. And then our third row, we're going to go 1 minus 1 is 0. 0 minus 2 is negative 2. 8 minus 3 is going to be 5. And then what do we have? 9 minus 4, that'll be 5 as well. And then negative 6 minus 1 is negative 7. Okay, so now what? Well, now, first column's done. We have a 1 here. We want to make this 2 and this negative 2. Let's make those both into zeros. Okay, so we're going to take row 1 and replace it with row 1 minus 2 row 2. And then row 3 will be row 3 plus 2 row 2. And that'll have the effect of turning the negative 2 and the positive 2 into zeros. So what do we have? Our second row is not going to change. So I'll just write that down first. 0, 1, negative 3, and 4. Okay, so let's fill this in. So for row 1, 1 minus 2 times 0 will still be 1. 2 minus 2 times 1 is going to be 0. We've got now 3 minus 2 times negative 3, that's 3 plus 6, which is going to be positive 9. Now we've got 4 minus 2 times negative 3, that's 4 plus 6, which is going to be 10. And then over here, we've got 1 minus 2 times 4, which is going to be 1 minus 8, which is negative 7. So that's your first row there. Now our third row, we've got 0 plus 2 times 0, so this will just still be a 0. Negative 2 plus 2 times 1 is going to be 0. 5 plus 2 times negative 3, that's 5 minus 6, which is negative 1. What else do we have now? 5 plus 2 times negative 3, that's going to be, well, that's the same calculation, right? So we'll have negative 1 again. And then over here we get negative 7 plus 2 times 4, that's negative 7 plus 8, which is positive 1. So that brings us here. And then now we'll turn this into a positive 1. So we're going to take row 3 and replace it with negative 1, row 3. Okay, and I'll do the next step up here because I'm running out of space. But that's okay, we're almost done. So the first 2 rows won't change. Oops, that should have been a, oh my goodness. That started off good. Everything was good up till that point. So that's going to be a 1, 0, and a 9, 10, negative 7. So I'm just copying the first 2 rows, 0, 1, negative 3, and 4. And then our third row is going to, the sign of every entry is going to change, right? So we'll have 0, 0, positive 1, and negative 1. Almost done. Because now we just need to clear out these 2 entries. So we're going to take row 1 and replace it with row 1 minus 9, row 3. And we'll take row 2 and replace it with row 2 plus 3, row 3. Okay, and that'll have the effect of clearing these 2 entries out. Okay, so what's going to happen? Our bottom row won't change. 0, 0, 1, 1, negative 1. Okay, and what's going to happen over here? So we're going to add row 3. Let's start. I guess I should do them in order. Row 1 is replaced with row 1 minus 9, row 3. So the top row is going to be 1, 0, and then 0, because 9 minus 9 times 1 is 0. Then we have 10 minus 9 times 1. Well, that's 10 minus 9, which is 1. And then we have negative 7 minus 9 times negative 1. That's negative 7 plus 9, which is 2. Okay, and then our second row, well, the 0 and the 1 won't change, but then this negative 3, we're adding 3 times row 3. So negative 3 plus 3 times 1, that's negative 3 plus 3, which is 0. This same calculation here, negative 3 plus 3 times 1 is 0. And then 4 plus 3 times negative 1, that's 4 minus 3, which is positive 1. So what that tells you now is, now you've got it, because this is this is essentially tells you what the solution to the first system is, because since this is the identity now, this will be the solution to the first system, and this will be the solution to the second system. So we can say therefore, and since I'm going to use row form this time, I'm going to say x1, x2, x3 equals 1, 0, 1. That is the solution to the first system. Let's label the first system as star, and the second system we can label it as double star. So this is the solution to star. And we can write down the solution to double star in a moment. So x1, x2, x3 is equal to, so I'll take these values now, 2, 1, and negative 1. Is the solution to double star. So that's how we can solve this. And if you're not, if this doesn't make sense, why this works, what I would encourage you to do is to try this example again, but just do the work of solve one system at a time. Just carefully solve this system on its own and see what you get. And take a look at your work, put it aside, and then do the same thing here. Now fully reduce this system. And I bet you won't even get halfway done, and it'll dawn on you that you're really just doing all the same steps again, and you're doing all the same work. So why not just keep track of what's going on and solve both systems simultaneously in the way that we've done here. So that's, if you don't understand why this method works, that's my suggestion to you. Try to solve these individually one at a time, and you can do it, right? It's about this much work times about roughly double as much work as we did here, but it'll be really illuminating as to why we did it this way and why this way is better.